Okay. Nomenclature, which is a fancy term for naming compounds. But it's not just naming compounds. It's taking the name that's given to a compound and writing the formula from it. So it's a two-way street. It works both ways. And the key word to keep in mind when we're discussing nomenclature is this. Non-ambiguity. Whenever we name a compound, we need to name it in such a way that that is the only name for that compound. And that if we take that name, we can only write the compound, the formula, one way. There are no ifs involved. Okay, so that's what the rules are designed to do. All right, so let's look at, we're going to start simple, which is always good. We're going to start with binary compounds. And in fact, it's not just binary, that is two parts. It's that the two parts are ionic in nature. That is, they interact as complete ions. But of course, all compounds are not ionic. And we'll discuss that in some later chapters. But this is where we start. The binary compound has two parts. It says two elements, but in this context, we're not talking about elements as in atoms. We're talking about elements as in parts, logical parts. So the first logical part could be an element, or the source could be an element, of course, but it's an ion when it forms the compound. And the binary compounds, if they're truly ionic, they will be composed of a metal first and then a non-metal, the second part. But there are binary compounds that are non-metals and non-metals together. But we're going to use the convention that we developed for the ionic compounds to help us write covalent compounds. Now, the difference between ionic and covalent is pretty simple. When you have an ion, there's a complete charge. For instance, sodium. That's a sodium ion. It has a +1 charge. Or it could be combined with the chloride ion with a -1 charge. And notice when you put them together, they cancel one another out. They neutralize. 1 +, 1 - sodium chloride, table salt, is neutral. But if we write something like carbon dioxide. Carbon dioxide is a nonmetal and a nonmetal. So that one can only be formed from covalent bonding. And covalent is a chemical word that we use to describe sharing of electrons. You don't have ions here. Electrons that form the bond are shared between the two. Okay, we won't get bogged down in that too much now. We're just trying to name compounds. So, we need to become familiar with the periodic table and where the metals and nonmetals come from, because the naming convention, the rules depend upon where did the metal come from, where does the nonmetal come from, which group does it come from? And remember, the periodic table is subdivided into, let's see, how about that? Into vertical groups. And that's where we're focused now. The vertical groups, for some of these groups, only have one possible charge available to them. The group that sodium is in, the alkali metals, is one of those groups. It always has a +1 charge. Whereas the halogens, of which chlorine is a part, they always have a -1 charge. Okay, so that's a good place to start. Type 1 compounds. Metal. Metal and non-metal. Okay. Focus on the metal. Can the metal have more than one charge? If it comes from the first group, right? If it comes from the first group, alkali metals, it can only have a +1 charge. If it comes from the second group, it can only have a +2 charge. And these are the alkaline earths. If it comes from this group, Roman numeral 3, boron, aluminum, gallium, indium, those can only have a 3+ charge and no other possibilities when they're bonded ionically. Okay? The nonmetals, if they're halogens, they have a -1 charge in a type 1 compound. The chalcogens, the oxygen group, can only have a 2- charge. The nitrogens, the nitrogen group, can only have a 3- charge. Now when we get to the difference, right, here's the +3 charge, here's the -3 charge. The carbon group is in the middle. They can go both ways. So we need special considerations for any members of that group. But don't be too concerned about those right now. We're talking about type 1 compounds. And if the metal comes from the first, second, or third group, it's a +3 charge and nothing else. So the metal has to be fixed charge. That's the condition for type 1 compounds. If it's a fixed charge, then it's simple to write the compound and balance the charges. We did it for sodium chloride. Well, what if we take something from the alkaline earth groups like calcium? Calcium's in the second group, so when it's in a compound, its charge will be 2+. Then suppose we combine it with fluorine, which is in the halogens. It's a -1 charge. Okay? That charge is not balanced. 2 pluses and 1 minus will not cancel and make a neutral compound. So you need 2 of them. So when you write the compound, of course, you don't put the charges in. There you go. That's calcium. And the first position is always the cation, the metal. Second position is always the nonmetal. The metal is named by the name of the element. That's it. Ca is calcium. But the nonmetal, you change the ending to IDE. So we would write this one, calcium. fluoride. Okay, let's do one more. Suppose we have one from the third group, say aluminum. It's going to be a 3+ charge. And let's combine it with something from the oxygen group, right? Well, let's just pick oxygen, right? Oxygen's a 2-. So how do we balance something like that? I mean, 3 pluses and 2 minuses, odd and even. The simplest way is cross multiply. Take the 2 over here and the 3 over here. So now you have 6 plus total, and here you have 6 minus. Now we have a neutral compound. The charge is balanced. Okay, so that's a type 1 compound. The metal is always a fixed charge. Type 2 compounds. Let's see, let me keep my slides moving here. Okay, type 2 compounds are still metals and non-metal. But the metal is a variable charge. So when we say variable charge, that doesn't mean that after the compound is formed, the charge of the metal can change. No, what we mean is when we form the compound, the metal could start out as 1 charge, or it could be a different charge, but it can't be both. Now, where do those metals come from? Most of those metals are from the transitions, right in here. Some of them are over here to the right of the transitions. Still metals to the left of that black zigzag line, but they're not group 1, 2, or 3. So anything else will be variable charge. Now, I say has the potential to be variable charge. There are some exceptions in here. For instance, zinc is always 2 plus. Silver is always 1 plus. Cadmium is always 2 plus. So for those, zinc, silver, cadmium, if you want to keep things simple, then you can follow the type 2 rules for even these that we know only have 1 charge. So let me finish type 2 rules. So what do? If your metal can have more than 1 charge, how can you balance it if you don't know what the charge is? Well, you have to know what the charge is. And when you write the name of the compound, you have to say what the charge is. For instance, let's say we have a compound called, let's write the compound first. Let's say it has manganese in it, and it has oxygen in it. And you're given the compound, and it's written this way, with 2 of these. Okay? How do you know what the manganese is? If this is the compound, you can deduce the manganese charge. Oxygen is always 2 minus. That means you have a 4 minus charge for the anion that must be balanced by the cation. So this one has to have a 4+ charge because there's only one of them. So a 4+ balances a 4-. Okay, now we know what the charge is on manganese and we can write the name. Now we say manganese. And then we put the charge in parentheses using Roman numerals. And then we just say oxide. Manganese 4 oxide. All right. Let's try another one. Suppose you're given this formula. No, suppose you're given this name. How about that one? Iron 3 oxide. Now, first of all, is that allowable? Well, you look at the metal, iron. Where's the iron come from? It's a transition metal, so yes, that is proper. So we're saying that iron has a 3+ charge. And we know that oxygen has a 2- charge. Now we need the subscripts so that we can balance the charges. So here we have another situation where we have an odd and an even. Cross multiply. So Fe2O3 is iron 3 oxide. Okay, one more type to go. Well, these are, this is a table that came out of your book. And these are the common cations and anions. Notice that some of them, like these, are fixed charge, right? Then when we get down to silver and zinc, those are also fixed charge. So you could name compounds of silver and zinc, well, actually cadmium also, with the type 1 convention, and you would be correct. But if you want to, for simplicity's sake, say they come from transition metals, so we're going to use the type 2 convention, I will accept that. Okay. So now, well, this is more detail that I've already given you on type 1 ionic compounds. Right? And these are some examples. Before we get to type 3s, we'll just look at a couple of these. Potassium chloride. Is that written correctly? K is potassium. Chloride is from chlorines, Cl. Now, is the ratio correct? Potassium is an alkaline metal. It's always +1 charge. Chloride is a halogen. It's always -1 charge. So yes, 1-to-1 balances the charge. What's the name of this compound? Well, you look at the metal, right? Where does the metal come from? Sr is what? I had you memorize that one. Strontium. Strontium is an alkaline earth, group 2. So it has a 2+ charge. And it can have no other charge, only that one. So that makes it a type 1 compound. You don't have to say what the charge is, right? I said non-ambiguity was the guiding principle. Also, not redundancy. In other words, if we said this, strontium if we said that, that's redundant. Of course, strontium is 2+ charge. It's an alkaline earth. Can't be anything else. So we don't put that in there because you're just saying the same thing over again. And you don't need it. So it's just strontium bromide. And the reason we have 2 bromines in that molecule is because there's only 1 minus charge for each that has to balance a 2+ charge. Okay? Okay, this is the same thing that I gave you, type 2 compounds here on the board. It's just in the slides for you for review. These are some examples of type 2 cations, right? Iron can be a 3+ or a 2+. Copper can be a 2+ or a 1+. Is that right? That's correct. Cobalt, SN, 10. Lead, Pb. Mercury. Mercury can be a 2 or a 1. Now, the weird thing about mercury is when mercury is in a compound, the mercury side of the binary is always 2+. So if you have one of them, like that, but if you have 2+ and it's only a 1+ for each one, you need 2 of them, right? That's something weird about mercury. It just does that. So when you combine the compound, this combined with chlorine then would be 2 there because it's minus. If we combine it with this one, you would need 2 chlorines also. But that means mercury is only a 1+. That's just the way it is. Remember when at the very beginning I said nature just does what it does. We discovered that this is how mercury behaves, so we have to deal with it. We can't change nature to suit our sensibilities. Okay. So here's some rules laid out in green. Some type 2 examples. There's one with copper. Sulfur. Where does sulfide come from? It's a chalcogen. It's in the oxygen group, right? So it always has a 2- charge when it's in an ionic compound, type 1 or type 2. Now, if we put sulfide in a type 3 compound, that's another discussion, and it's coming. Okay. All right. What is this one called? CrO2. Well, you have to know what Cr is, right? Cr is chromium. So you take that one and you say chromium. You know where chromium comes from. It's a transition metal. So you leave a space for the charge because you don't know the charge yet. And then it's combined with oxide. Okay, now we need to determine what is the charge on chromium. Each oxygen is 2-. So the total charge, negative charge, is 4-. We only have 1 chromium, so it has to be a 4+. Okay, that's the name of the compound. And if you have that name, you can write CrO2 with no other possibilities. Okay, let's complicate things. Why don't we? We want to name the compound that results from the most stable ion for sulfur, which is 2-, and the metal ion that contains 24 electrons. Okay, it's going to make some detective work. We know we got sulfur, and we know we have a metal, and the metal has 24 electrons. Now, there's one thing in this problem that's not stated explicitly, but it's understood. We're forming this compound with only one metal atom. Okay? The most stable ion of sulfur and the metal ion that contains 24 electrons. So we're assuming that there's only one of them. Otherwise, we're lost. I mean, we can't answer the question, because if there are 2 or 3 or 4, we don't know. So we have to assume that there's only one. So if it's got 24 electrons, what's the charge that it has to have? If there's only one of them, it has to be 2+, right? So if it has 24 electrons and the charge is 2+, how many protons does it have? Well, it needs to have 2 excess to be a 2+. So that means it has 26 protons. You look at your periodic table. Let's see, we'll go down, let's see, 26. Oh, there it is. It's iron, Fe. So it's FeS. Oh, wait a minute. What's the correct name? Okay, sorry, I didn't finish answering the question, did I? If it's FeS and the charge is 2+, then we say iron 2 sulfide. Okay? Let's see. Yeah, we're doing good. Okay, type 3 compounds. Type 3 compounds are formed between 2 nonmetals. So I need some room, so I'm going to erase this type 1 and type 2. Okay, type 3. Non-metal, non-metal. All right. The thing to understand about non-metal, non-metal compounds is there are no ions, but we use the binary ionic convention in naming. So we put one of them first and the other one second becomes the ion look-alike. Question is, which one comes first and which one comes second? Generally speaking, the first one in the binary is the one that's to the left of the other one, right? Because it will be less electronegative and more metal-like. It's not a metal, but it's more metal-like. So it occupies the first position. That's generally true. There are some exceptions. But let's take an example. Let's see, carbon dioxide. Carbon is to the left of oxygen, so that one fits. How about this one? Water. Hydrogen's to the left of oxygen. How about this one? Phosphorus is to the left and down from oxygen. So those hold to a convention. All right. So if they're not charged, we can't say that they have a charge in the name. So what we have to do is simply say, how many of them are there in the compound? We name them similarly. Like the first one in the name is just the element name. And the second one changes the ending to IDE. We need prefixes in the name that say how many. And we use the Greek prefixes for the numbers. Let's see. Here we go. So mono means 1. Di means 2. Tri is 3. Tetra is 4. Penta is 5. Hexa is 6. Hepta is 7. Octa is 8. Let's see. No. There are 2 more. Nona is 9. Oops. And deca is 10. That's as high as I'm going to go. So how do we use them? Well, let's take carbon dioxide. We know that this is the way the compound is written. CO2. So we say carbon, di for 2, oxide. Okay. Notice that for the cation, well, the lookalike, the first one in the name, if there's only one of them, we don't say mono. It's kind of redundant. Just doesn't sound right either. So we know that if we have one of them, if we say carbon, there's at least one. Otherwise, we wouldn't say it, right? We wouldn't say carbon dioxide. Oh, I'm just kidding. There's only oxygen here. There's no carbon. No, if we say carbon, there's one at least. So carbon dioxide is correct. How would we name this one? CO, right? That's the one that'll kill you. Well, carbon dioxide will kill you too, but carbon monoxide will kill you a lot faster. So we say carbon monoxide. Notice we don't say monooxide. It just doesn't sound right. So we drop one of the O's because we've already got an O. So monoxide is the proper name for this compound. Okay. How about this one? I wrote this one before. Right? That compound exists. We know it is there, right? You find it in every fertilizer bag. So we say diphosphorus pentoxide. Notice we don't say pentaoxide either. Chemists have ears, and if it doesn't sound right, then we make allowances. So you drop the A and just add pentoxide. Sounds better. Okay, so that's how you name type 3 compounds. First rule, they have to be non-metal, non-metal. Then you say, how many are there? Now, if we have the name, it's simple to write the formula, right? we need 2 phosphorus and 5 oxygens. Okay? All right, let's take a look at, let's see, I need to back up. Sorry, I skipped. No, I didn't. Must be the next one. Examples, here we go. We did carbon dioxide already. Sulfur is the first one. And then fluorine is the second one, which means we change the ending to IDE. And 6, the prefix for 6 is hexa. Sulfur hexafluoride. You're done. Or if we have sulfur hexafluoride as the name, you know to put the S first, the F second, with a subscript of 6. Dinitrogen tetroxide, right? 2 nitrogens, 4 oxygens. How about this one? SeO2. So what is Se? Well, you might have to dig for that one. That was one of the ones that you need to memorize. Se is selenium. Right? So how do you know to name this one? What you need to do is look at that first one and ask yourself a question. Is it a metal? If it's a metal, then you have to choose between type 1 or type 2. If it's a non-metal, then it's automatically type 3. Okay? So it's selenium. Since it's type 3, selenium dioxide. Okay? And in fact, selenium comes from oxygen's family. It's just a couple of positions down. It is a chalcogen, right? So we have marriage inside the family. It's okay in chemistry. Selenium dioxide. Okay, so here's a decision tree. If you like this stuff, you have a binary compound. That means it has 2 parts. Is there a metal present? If yes, then you've got to decide, is it a type 1 or a type 2? And the decision that you make depends on where does the metal come from in the periodic table. If it comes from alkaline metals, alkaline earths, or the boron family, which has boron, aluminum, gallium, and indium, then it's 3+, and it's a type 1. If it comes from any place else, and it's still a metal, then it's a type 2. Except for those 3 exceptions that I mentioned earlier. And then you can choose between type 1 or 2 and how you name it. If they're both nonmetals, then it's automatically type 3. And you have to use the Greek prefixes to say how many are there. All right. Now, if that's not enough, I got another curveball to throw at you. For type 1 and type 2 compounds, there's another possibility. There are a group of ions that are composed of more than one atom. They may even be viewed as a compound of themselves, but they form ions. They're called polyatomic ions. Poly meaning many. Many atoms form this group that behaves as a single unit. So in those cases, all but one of them is negative, so they occupy the anion position, the second position. and they have names, right? So you have to know the names. The slide says memorize the names. If you use them enough, you'll remember them. But I've also included a chart in the review document, and it will be available on exams so that you can look them up. But that's not the whole story. You have to recognize that you've got a polyatomic before you can go looking for it. All right? So you've got to use the table at least in order to get familiar with it and to recognize a polyatomic when you see one. These are some examples. Notice that all are negative except for one. This one's positive, ammonium. So this would occupy the cation position, the metal position, and it can only have one charge. This is the only possibility. So what convention would you use? Type 1, of course, because it can only have one charge. And if you combine this with any anion, the anions could be derived from elements, right? Could be from over here somewhere, or it could be one of these other polyatomics. And they are always fixed charge. If we say nitrate, we mean NO3-, nothing else. If we say carbonate, we mean CO3 with a 2- charge. That's it. Nothing else can be that name. Some of them form logical groups. And what I mean by that is, in this case, you've got a halogen here, and it's combined with various numbers of oxygens. 1 here, 2, 3, 4. It's like a family. The only difference is that you change the number of oxygens. The charge stays the same. And when you change the number of oxygens, you change the name. And I'm going to talk about that a little more in just a second. Okay, here's what that table looks like. Right? All of these polyatomic ions on the left-hand side are sorted by their names, alphabetically named. So acetate will be first, on down through thiosulfate. And then the formulas are given to the right here. Then the same data, all of these members are reshuffled on the right-hand side so that they're organized by alphabetical by formula. So ASO323- is arsenite, and it's first, not acetate. So you got two ways to look them up. Everything on the left is repeated on the right, but in different order. Okay, so that's the one that you'll have access to in the review document and on exams. Okay, so what do we do? For this example, what is that one? Well, first of all, how do you recognize polyatomics? For all of the negative ones, well, not all of them, many of the negative ones, you always have an oxygen involved. There are a few that have no oxygens, like cyanide, Cn-, doesn't have an oxygen. So you just have to remember that one. But if you see multiple elements and an oxygen, then you should suspect polyatomics. And then this one, you just need to memorize that one because it's the only positive one in there. So just memorize it. I mean, how hard can it be to memorize one? That's ammonium. And we use, like I mentioned before, we use naming conventions of binary compounds, type 1 or type 2. Right? Because they're always ionic, pluses and minuses. So it's always type 1 or type 2. It depends. If you have a metal in here, then you have to ask your question, is it a fixed charge? Is it variable charge? And then you use the the name that's given to the polyatomic anion that's combined with it. So this is ammonium acetate. That's the acetate ion. This is the ammonium ion. That's it. That's all you have to say. No Roman numerals, because this can't change its charge. Okay, here's an example. Sodium hydroxide. There's the sodium. There's the polyatomic hydroxide. And if you use liquid plumber, or if you're old like me and you remember when drain cleaners came in bottles, then they were solids, you could shake them and hear them rattle, then those were pure sodium hydroxide. They don't sell that anymore, I don't think, because it's too hazardous. So they make liquid plumber, which is a solution of sodium hydroxide, plus other additives. Magnesium nitrate. All right. So with magnesium nitrate, what are we getting at here? This illustrates the fact that nitrate is a single unit. You cannot break it up. So if nitrate has a -1 charge and this is a 2+ charge, you can't write it that way, right? If you need 2 of these negatives, you have to hold it together in the single unit and use parentheses to get more than one of them. So for polyatomics, you always have to have that parentheses, which is really fortunate, right? Because if you have the formula and you're trying to name it, and there are more than one of them, then they're going to have parentheses, and the parentheses is going to say, this is a polyatomic. So in that case, it's good news, because it tells you that NO3 is a polyatomic. You just need to go look it up and find out what the charge is. Actually, you don't even need that, because we know magnesium is a 2+ charge and nothing else. But to name it, all you have to say is magnesium. It's a type 1 compound. Magnesium nitrate, that's it. With that information, you can write the compound formula with no mistakes. It'll only be one formula. No other possibility than Mg parentheses NO3 taken twice. Here's one that has 2 polyatomics. Ammonium, which is a +1 charge, and sulfate. Look it up, it's a 2- charge. So we need 2 ammoniums. And ammonium is only one possible charge, so we don't have any Roman numerals. It's just ammonium, sulfate, you're done. Now, in this case, we have a transition metal, iron. So we have to deduce what is the charge on iron. So you need to know what is the charge on PO4, phosphate. It's a 3- charge. There's only one iron, so the iron has to be 3+. That's where you get the Roman numeral 3. Okay? How about the name of this one? KClO3. First question is, do we have a polyatomic there? As a matter of fact, we do. Right? We have 3 elements here. One of them is oxygen, so we should suspect this one is a polyatomic, ClO3. We have a metal. Where does it come from? It's an alkali metal. It can only have +1 charge. That's it. And we can deduce from the formula that this one has a -1 charge, that group. We just need to know what is the name. So go look it up. Potassium. And ClO3 is chlorate. That's it. Potassium chlorate names the compound. No other possibilities. Okay, which one of these are named correctly? So we got a mix of type 1, type 2, and type 3 compounds. So we got to know our rules and apply them for the proper names. So the first one, P2O5. P comes from where? It's a nonmetal. Both of these are nonmetals, so we use type 3 convention. Diphosphorus pentoxide is correct. ClO2. So where do those come from? Chlorine is a nonmetal, oxygen's a nonmetal. That's also a type 3. Now don't get this confused with one of the polyatomic ions. This is not an ion. This is a neutral compound. If we had it combined with a metal, then maybe you could consider it as a polyatomic ion, but in this case it's not. It's a neutral compound that needs the type 3 convention. Chlorine, since it's first, we don't say mono. It's just chlorine. And then this should be dioxide because there are two of them. That one is wrong. How about PbI4? Well, what is Pb? Pb is lead. It's a metal. So this is either a type 1 or a type 2. Where does lead come from? It's not one of the alkaline metals, alkaline earths, or the boron group. So it's a type 2 compound. So we need the Roman numeral charge on lead. We know the charge should be 4 plus, Roman numeral 4 for 4 plus because iodine is a -1 and we have 4 of them. So we need a 4 plus for lead to balance those negatives. We need a Roman numeral 4 in here. It's not there, right? So that's wrong. How about this one? Where does copper come from? Well, let's see. Copper is an alkali metal, transition metal. So a transition metal needs a Roman numeral. Is it the correct Roman numeral? SO4 is a polyatomic ion called sulfate. It has a 2- charge. So copper has to be a 2 plus because there's only one of them. So that one's wrong. The only correct one is the first one. Right? The rest of them are wrong. Okay. Now, before we get to naming acids, let's talk about those logical groups of polyatomic ions. I had one that was boxed in. It was formed from chlorine and oxygen. So that's a good place to start. I start here. ClO3 minus is chlorate. Take away an oxygen. Change the ending from ate to ite. Okay, take away another one. We don't have any more suffixes that we can use. Ate and ite is all there is. So now we need a prefix. So we want to go less than ITE. One less. So we use a medical prefix, hypo, like hypodermic, under the skin. We're going under ite. Hypochlorite. So we have chlorate, chlorite, hypochlorite. We can go one the other direction. But we need a prefix here also. And the prefix that says above or more than is per. So it's one above the chlorate, per chlorate. Okay. There are two other groups that can use this exact convention. And they're formed from halogens. Right? If we use, instead of Cl, we use Br, then substitute Br for each one of these, and you say bromate, bromite, hypobromite, perbromate. Or we can substitute another halogen, iodine. So we would say iodate, iodite, hypoiodite, periodate. So if you know that sequence, you've got 12 of them already memorized. Now, fluorine doesn't fit. It's a halogen, but fluorine doesn't form these types of polyatomics. Okay? It's just those three that we're interested in. Now, there are other examples, but this is the biggest group, these four. There are others that most of them only have two. I probably shouldn't have erased that, but now we're going to talk about acids. Acid naming convention is sort of grandfathered in from the Middle Ages, from alchemy. And we just tried to standardize the naming convention. So, here are the rules. Acids are recognized by a hydrogen as the first element in the compound. HCl, for instance. Going to have a hydrogen first. Sometimes they have 2 or 3 hydrogens first. For instance, like that one, or like this one. Okay, but the hydrogen is always first. We put the hydrogen first because when we put it in water, when it goes into water, it dissociates. Sometimes completely, sometimes partially. And makes that plus in that case. Okay? Only when you put it in water does it do that. If it's not in water, then HCl is a gas, and we name it with the convention hydrogen chloride. But when it's in water, it makes this acidic solution, and we give it another name. Now, the rules are whether or not there's an oxygen in the molecule. All right, so for this one, there's no oxygen. Anytime there's no oxygen, you start the name with hydro. Okay? Start the name with hydro. Then you take the, what would be hydrogen chloride, and you change the chloride to chloric. Followed by the word acid. Okay, so the key here is, first of all, is it an acid? It's got a hydrogen, it's in solution. No oxygen, start it with hydro. and then change the chloride to IC, chloric, hydrochloric. Okay. The next one, this HCN involves a polyatomic ion. If it's not dissolved in water, it would be called hydrogen cyanide. Dissolve it in water. Now it's no oxygen, so it has to be hydro. And the cyanide, ide becomes ic. Okay, hydrocyanic acid. Here we have one, H2S, right? If you've ever been to Sulphur Springs out in Greenbrier County or thereabouts, you know what hydrogen sulfide smells like. Hydrogen sulfide gas, not in solution, H2S, is just that, hydrogen sulfide. Put it in solution, then you call it by its acidic name. No oxygen, hydro, and instead of sulfic, sulfide becomes sulfic. Just doesn't sound right. So we extend the name to sulfuric acid, hydrosulfuric acid. All right. So these are some other examples. Hydrobromic, hydroiodic, hydrofluoric acid. Hydrofluoric acid is, if it's concentrated, is extremely dangerous because for some reason, if you put a drop on your skin, it just keeps eating away at the tissue until it goes all the way through. It just never stops. So that's the danger with hydrofluoric. I've used concentrated hydrofluoric very carefully. Okay, so what if there's an oxygen there in the anion? Well, it depends on the name of the anion before you make an acid out of it. Okay, if there's an oxygen, you don't start the name with hydro. Right? If there's an oxygen there, no hydro. So in this case, you've got oxygen, and let's just assume that it's in solution. It's in aqueous solution. We've got the hydrogen here for our acid. Then you look at the polyatomic. The polyatomic is nitrate. You don't say hydro, so just start with the polyatomic name. It would be nitrate ion, but since it's an acid, we change the ATE to IC. So HNO3 becomes, well, that's not proper. Let's just say it's nitric acid. Like that. Okay. Another example. Remember when we only had H2S, and that was it? That was hydrosulfuric acid. If we add this oxygen in here, now we've got a polyatomic sulfate ion, and the 8 becomes ic, and the hydro drops out, no hydro. So we just say SO4 is 8 becomes ic, sulfuric acid. That's it. So that's one that's easy to get confused. If you accidentally put a hydro in front of sulfuric, then it's not this one anymore. It's the H2S that we looked at in a previous slide. How about this one? Here's a polyatomic, C2H3O2. That's the acetate ion. And we change the ate to ic, it becomes acetic acid. Notice that the first letter is hydrogen, the first element is hydrogen, but you've also got hydrogens over here. So what are those hydrogens doing? They're stuck. They cannot leave the molecule. They cannot leave the compound. In other words, when we have this one, that one can do this plus this. But those hydrogens never dissociate. They're stuck in the polyatomic ion. Now, everybody knows acetic acid, right? Buy a bottle of vinegar, it's 5% acetic acid. So everybody knows what it smells like. Okay. What if instead of ATE, we have, instead of ATE, we have ITE. So this example, HNO2. Now we have a close relative of NO3, but it's not nitrate anymore, it's nitrite. For acid naming conventions, the ites become us. So instead of nitric acid, this is nitrous acid. Okay, ates become ix, ites become us. Right? Same thing with the sulfate, SO4, sulfite is SO3, and it becomes sulfurous acid. Still oxygen, no hydro. Go back to that group that we were talking about earlier. We started off with ClO3 as the chlorate. This is chlorite, so that would be chlorous acid. If we had ClO, HClO, right? That one starts out, this anion is hypochlorite. So the acid would be hypochlorous acid. Okay? These are some common and useful acids. Actually, excuse me. This one is very useful, important. H3PO4. This one has 3 acidic hydrogens on it. And PO4 is phosphate. Ates become ix, phosphoric acid. And of course, all of these are in solution. All right, so there's your decision tree if you want to use one, something like that. So let's see. I'm talking to you. Sorry about that. It's my cat again. One of them. That particular one is incorrigible. Okay. So We're not talking about acids anymore, are we? Well, maybe we are and maybe we aren't. Right? That's not an acid. That's not an acid. That's not an acid. That's an acid. What's this one? That's a base. For bases, you don't have a special naming convention. You just name it like it was a compound, and it just happens to be dissolved in water. So that's convenient. We don't have to learn a whole new set for bases. When this goes into solution, the hydroxyls come off as a single unit and do their thing in water, which we'll talk about in a later chapter. Now we want to see, are they named correctly? KNO3. All right, what do you have here? You have a metal, right? Actually, it's a group 1 metal, only one possible charge, which means type 1 compound. Now, what else do you have? You have a polyatomic ion. So what is it called? NO3, look it up, is nitrate with a -1 charge and a K with a +1 charge. Type 1, we only have to say potassium nitrate. That one's correct. This one, Ti, is titanium. That means, since it comes from the transition metals, it could have variable charge. So we say, all right, what is the charge? Well, oxygen is a 2-, so it's 4- that has to be balanced by the cation, which should be 4+. That name is wrong. Titanium 4 oxide would be correct. SNO4, SNOH, parentheses 4. Right? We need the parentheses because OH is a polyatomic ion. And 10 is not group 1, group 2, or group 3, so it has to be a type 2 compound. So 10 could have a variable charge. So what is it? OH hydroxide is a -1 charge, taken 4 times is 4-. The 10 should be a 4+. 10, 4 hydroxide is correct. PBr5, what do you have there? You've got 2 nonmetals, a type 3 compound. So we say, just name it. Phosphorus, pentabromide. That's correct. Now we have hydrogens leading off. This is an acid. We have to assume, of course, that this is in solution. It doesn't say that it's in solution, so we have to assume, since we're comparing it to an acid name, then we have to assume that it's in solution. So oxygen means no hydro. What is the polyatomic origin? SO3 is sulfite. Ites become us's. So sulfurous acid is correct. Right? So that's the only incorrect one in this group. Needs to have a Roman numeral 4 there. Okay, write sodium hydroxide. There you go, sodium and hydroxide. We know that's correct because sodium is a +1 charge always. It's a group 1 alkali metal. Hydroxide is fixed as a polyatomic at -1. Sodium hydroxide is the only possibility, NaOH. Potassium carbonate, right? What type do you have there? Potassium is an alkali metal. It's a +1 charge. Carbonate, there's potassium. Carbonate, look it up, CO3, 2-. So we need 2 positives to balance the 2 negatives. K2CO3. All right. How about sulfuric acid? We know that it has oxygen in it because it doesn't start with hydro. So we look for sulfuric. What was its origin? Where did ick come from? Ick comes from 8. So the sulfate is the origin of sulfuric acid. Right? And if it's an acid, it has to have dissociable hydrogens. So we need hydrogens are +1. Like that. Okay? Now, there are cases where hydrogen can be negative. Let's see. In that case, hydrogen will be written as in the anion position. For instance, let's see. Trying to think of I don't want to just invent a compound that doesn't really exist. So I'm saying okay, a lot of dead air there, sorry. Well, I'm sort of falling short here. I was going to give you one with hydrogen as the anion position. So I need I can't come up with a good one right now. Save it for later. Dinitrogen pentoxide. The fact that you've got prefixes in here should be a giveaway. Plus, you've got a nonmetal and a nonmetal. So this is a type 3 convention. All you have to do is just say, what are the elements and how many of them are there? Okay, that's it. Now we see a Roman numeral, type 2 compound. I mean, is that allowed? I mean, is that reasonable? Is it correct? Well, look at cobalt. Where does cobalt come from? It's a transition metal. So yeah, that's reasonable. Does it work? Well, we have cobalt, and it has a 3+ charge, and we have nitrate that has a 1- charge, right? So how many nitrates do we need to balance the 3+? So let me write that a little better. That O's too big. There we go. We need 3 polyatomic ions to balance the cobalt. Okay? All right. Okay, we're doing good. I think I got 30 minutes left. Yep. Okay. Let me be sure I'm not. Actually, we're almost done. Okay. So a compound has a formula XCl3. All right. Where X could represent a metal or a nonmetal. Yeah. So what could be the name of this compound? Well, if it's a metal, then it depends on the charge, right? The charge would have to be 3+, right? Because this is 1-. This would have to be 3+. So this could be, it could be boron, could be aluminum, right? If it's a nonmetal, then it could be phosphorus, right? Or it could be arsenic. So I'm kind of confused as to what the, oh, we have choices, right? I forgot. So which one of these would fit? Well, magnesium chloride wouldn't work because magnesium is a 2+ charge, right? So we would need 2 chlorines. Tin-4 chloride is a 4+ charge on the tin, so we'd need 4 chlorines. That won't work. Monochloride won't work because we need 3 of them. So phosphorus trichloride is the only one that would work, this one, out of this selection. And it is a type 3 compound in that case. Okay, one other point. Some compounds, solids, tend to attract water molecules into their structure. But when they do that, the water molecules do not rearrange to make individual hydrogen bonds with hydrogens bonded with some and oxygens bonded with another. They retain their character as water molecules. They're just bound to the structure of the ionic compound. These are called waters of hydration. Okay, so how do we write those? When we know that there is water there, well, in the first place, how do we know that we have extra water there? Well, what's the boiling point of water? Right, 100 degrees Celsius. If it's bound to a compound like this, then we need a little bit more heat to get it off. Like usually 105 degrees will do it. So you dry the compound at 105 degrees and you weigh it before and after. You find out how much mass it lost. You can even analyze it and see, okay, it's still got the same ratio of metals to non-metals. For instance, okay, so you can have this compound, and you know the ratio of that to that is fixed. So if you analyze it before and after, you find the same ratio. So it lost weight some other way. And if we heated it at 105 degrees, you can logically assume that it's probably water. But how do we know that there's more in there? There's not some more water attached. Well, you heat it at a higher temperature. Usually 150 degrees is good enough for most of these types of compounds. And now you get to the point where it's just that and nothing else. So if you analyze it, you only find zinc, sulfur, and oxygen. There's no hydrogen involved. Of course, there's less oxygen because you've lost water. But this is called anhydrous. Because there's no water. But water will attach itself to zinc sulfate, and it attaches usually in a definite ratio. So when we say how many waters of hydration are there per molecule, so to do that, we need to know what was the loss of mass in the process from before and after.
I'm sorry to interrupt you, Professor, but my laptop just died and I just rejoined the chat.
Okay. Do we need to do anything?
No, I was just letting you know it happened about 3 minutes ago. I was just letting you know I was back in here.
Okay, okay, good. Yeah, I see you there. So these water molecules are part of the structure of the compound, but they're not in the ionic structure itself. They're separate and they're bound some other way. So how do we show that? Well, when we write the compound, we separate the compound from the waters using that dot. It's not a period, it's a dot it's a midline dot. And then we put how many waters are there. In the case of this compound, there are 7 of them. Okay? So how do you name it? Well, you name it by convention. How would you name this compound? Zinc. And this is one of those that has a fixed charge, right? So we could say zinc 2, or we could say just zinc. And then sulfate. Okay? Then you say how many waters are associated with this. Well, we use the same Greek prefixes. 7 is hepta. So we say hepta. And the word for water in this case is hydrate. So there's the name of that compound. Zinc sulfate, heptahydrate. And we know from convention that with this out here, that these waters are separate. So you write this one first, and then you put these up here, separated by a dot. Okay? You see some of those like that. Another possibility. So that would be copper sulfate pentahydrate. Oh, here's a good one. Everybody knows wallboard, right? What's in your walls? Gypsum. Okay, this is gypsum. Now, calcium hydrate, anhydrous calcium sulfate, has no water. But gypsum has 2 waters of hydration. So it would be calcium sulfate dihydrate. Okay? All right. So that covers all the naming conventions that you're going to need for quite some time. Type 1s, type 2s, type 3s, acids, and hydrates. So I'll stop the share and open the floor for questions or comments. Okay.
Professor, does this have seem to 1050 or 1150? Because I thought on my schedule it said 11.
You know, you're right. I finished early. These are the only 2 chapters that we're going to cover for this upcoming exam. So what we can do is, if you don't have any questions, has everybody looked at the review document yet? Nobody's looked at the review document.
I have not looked at it yet, Professor.
I suggest that you look at the review document. It will make a huge difference on how you do for the exam. If you take the review document and work those problems, then you will be in better shape for the exam. I can show you where that is. Let me call it up. Let's see. It's going to be here. All right, so let me share my browser. Share, where is it? Here it is, share. And I want to share my browser right here. All right, that's not what we want. And what we want is, not that one, this one. Okay, Blackboard, of course. Let's go in the course. There we go. And then you go down to the appropriate lessons and reviews. Here we go. And this will be exam 2, Chemical Foundations and Nomenclature. By the way, for this exam, in this chapter, you have 2 extra credits that are possible, right? Know the periodic table. You can complete that one. You just go in here, you right-click it, and save it as. Then you'll need to print it out and complete it by hand, preferably using colored pencils. They work the best. And then when you come back with you photograph or scan your document, you can either submit the image, or if you have the capability, convert it to a PDF and just say here, browse your computer for your finished document and attach the file. And then down in the lower left-hand corner, you've got submit. Okay. So that one, let me go backwards here. Let's see. Here we go. Let's go back. The other extra credit that you have is 50 ways to name your compound. So this is an exercise in naming compounds. It'd be good practice. So there's your document, and it just gives you a combination of names and formulas. If it's a name, you write the formula. If it's a formula, you write the name for the answer. And there are 50 of them, so each one's worth 2 points, or 2%. And submit it the same way. This document, see it says savable right here? If you download that document to your computer and then open it with your reader, your PDF reader, then you can fill it in and save it and submit that document. You don't have to print it off and fill it out by hand, which you can do. That's fine. But if you have the capability and the desire, you can do it completely in your computer. You just have to figure out how to do subscripts and superscripts. And in your PDF reader, if you hit Control E, you'll get an editing bar at the top that'll allow you to do superscripts and subscripts. Okay, so I just want to mention those extra credits. Now for the review documents. Right. So you go down to here, Exam 2 Review Document. Right. So there's your review document with no answers in it. Right. Then here's the review document with the answers. Right. And also, here's another document that's in my handwriting, as legible as I can make it, how you work the problems. It'll have most of them. Some of them I leave out because they're simple memorization, and there's really no way to explain that. But these review worked problems are a separate document that will show you the logic behind the answer to the question. So you've got these 3 possibilities. My students in the past have taken this fillable form and just treated it like an exam. It looks exactly like an exam. It doesn't look like a Blackboard exam. It looks like a paper exam that I would give you if we were face-to-face. But you just fill it out and then grade it against this key and see where your weaknesses are. and focus on those items. If you can't figure them out, go to the work problems, and that'll help you. You still can't figure it out, then you come to me.
Speaking of exams,
Yep.
my exam 1 still has the password on it. So should I keep trying?
It's not supposed to.
Hold on, let me show you my screen.
Okay. Let me stop my share.
Yeah.
Oh, well, I'm on my phone, so I can show you on here. My laptop.
Is anybody else having that problem?
No, sir.
Yeah. You should be able to share it. You see that green arrow at the bottom of your screen?
Yeah, I'm on my phone, and because my laptop's broken right now, so I was using my dad's laptop.
Oh, okay. So let
Yeah.
me. I've still got you in the thumbnail. Let me
And he can't get
make
the
it big
Zoom
so I
on
can see
his
it.
laptop.
Okay. Yeah.
Oh no.
It's still asking for a password?
Yeah, on the exam 1.
Yes,
That
sir.
should not be there. Hold on a second. I'm going to
Okay.
share mine. And I'm going to go. I'm going to go to the. Come on. Here we go. I'm going to access Respondus Monitor Lockdown Browser. Here we go. So you get to see what the instructor sees. So go down to exam 1. Here we go. There's exam 1. Settings. Right. Lockdown browser is required, but the proctoring, the monitor, is not required anymore. You don't have to have a camera. And there's no password. It should not be asking you for a password.
Oh no.
Yeah, it keeps telling me the same thing too, sir.
All right. Okay, here's what I'm going to have to do, because we can't wait to fix it. Is I'm just going to have to take the lockdown browser out of the equation. So here's what I'll do. I'll just say don't require either one for this exam. Okay. Now you should be able to go in through your standard browser and into Blackboard just like you would normally do, and click on that exam and take it. So I'm depending on you guys to be honest. That's all there is to it.
Let's see.
If it's not going to work for you, I don't have any choice. That's the only way we can do it.
Yeah, I don't know why it's doing that.
Yeah, maybe by the time we get to the second exam, I can have our IT department figure out what the problem is.
All right, I can get into it now.
Okay. Let's see. Oh, let's go back to the review document. Lessons and reviews. And we'll go into the next exam. See, there's another learn these element symbols. So that gives you the periodic table that outlines which ones I want you to memorize. There's a link to your homework. Let's see, here, review documents. Right. So in this folder, I've also got this common polyatomic ions separated, periodic table there. And these are the focus of your efforts. Right. So in order to use these, you need to right click and save the link as. That will give you the document on your computer, and then you can load it into your reader. If you try to play with these documents in the browser, they don't work too well. It needs to be downloaded and then opened in your Adobe, your Acrobat reader. Okay? So that's where you need to focus your efforts. If you can work these problems, answer all these questions, then you should do fine on the exam. There should be no problem at all. Let's see, let me pick up this mess. It's okay, guys. I have to sit too close to this thing, and sometimes I knock it down. And the cats just scatter. Okay. Well, any other items of business we need to deal with? Because we're really early. Let's see. Melinda, are you having any luck with your getting registered with OWL with your homework?
No, not yet. They responded to me with an email and told me that I needed to go in and have them resend it to my email for the activation code. Well, I did that and they still haven't sent me an activation code yet. So I don't really know, but I'm still trying.
Did you get in touch with D Frederick?
Well, I emailed her that evening when you and I spoke.
Right.
And then I had an email. I don't assume it was her. I'm assuming it was somebody else who responded to me.
Oh, she forwarded it to somebody. Well,
Yes, sir.
if you try to connect with tech support directly, half the time you don't get a response. So that's a good sign. If you contact her, then she rattled somebody's cage and they got back to you.
Right. Okay.
I can't remember. Were you the student that I sent screenshots of the homework?
Yes, sir.
Okay. Okay. I lose track of who I'm talking to sometimes. Okay, that's good. Do I need to do it also for the second exam? Maybe I should do that too. If it's going to take them extra time to get, because the second homeworks are due on the 11th. Well, that's 7 days. So let's wait a couple of days and see if they respond and get you that code that you can log in.
That's fine. Thank you.
You know, the odd thing about it is you're not supposed to need a code. If they've got you, if you've purchased the product, then you're in their system, and my Blackboard course is linked to the homework. You should be able to enter through Blackboard into OWL and just do a registration thing at the beginning, and then you're done.
Yeah, I didn't need a code either.
Yeah, you shouldn't need a code. So
that's what it's telling me.
okay, hold on a second. Let me go to.
It took me forever to get the OWL going, but it's like you had to unblock other I don't know, you had to unblock something to allow the OWL to pop up.
Oh, your pop-ups.
Yeah, you have to do that.
In your browser, you have to enable pop-ups. This is Firefox. It should be reasonably similar in other browsers, but if you let's see, am I still shared? My browser's still shared, isn't it?
Yes, sir.
Okay, so if you go in, I click this this 3-bar thing up in the right-hand corner, and you should go into options, I believe. I got stuff in the way, so let me move it out of the way. Options, here we go, with that little gear sign. And then you should go to something, depending on your browser, something having to do with security. And scroll down till you find pop-ups. Let's see, pop-ups. Here we go. Mine is right here under permissions. Block pop-up windows. If I had that checked, I would not be able to get into OWL. So you have to uncheck it and allow pop-ups.
Maybe that's the problem then. I'll try that.
Yeah, well, we're grasping at straws, so that's as good as any. So if I go into, let's see, if I go into my homework link, this is one way to get into it. This is where I would go for registration. But after you get into lessons and reviews, individuals, I've got links in there for the individual chapter homework. So you sort of skip a step. But this is where it takes me. Is that showing? Is my pop-up showing? Cengage loading content. It's not showing?
No, sir, I don't see anything.
You're just seeing my browser then, right? Okay, so let me stop that share and share the pop-up, which is, let's see, where is it? Here it is. Now, you should be able to see it. So here I can see my users, right? And I don't see, you're not in there. So sometimes I've gone in and looked to enroll users if their names are there, but they're not officially enrolled in the OWL homework, then I can fix it there, but that won't work for you. And then I see my grade book. This is where I get all the grades, right? So I won't stay there too long because I don't want you to see each other's business. And then some of them are graded and some of them are not. So when they say graded here in the parentheses, those are the ones that you focus on for grading. The other information here, all these other things are there to support. So you have access to them. Some of them have little quizzes that let you know if you're on the right track, but they don't enter into your course average. Just the ones that say graded are the ones that I'm concerned with. So I don't see anything else that I can do from here. We've got to get you into the course. I would stay after D. I wouldn't wait 4 or 5 days just for a response. I would say after 24 hours, if you hadn't got a response, contact D and say, they tell me that, say to D, I'm told from tech support that I need this activation code, but my instructor says I don't need it because I'm going in through Blackboard. Say, what should I do? You know, put a question to it so she has to answer.
All right.
Okay. Yeah. Get in touch with your bulldog.
Right.
Make them answer the questions. I mean, we're paying too much money for this service. Well, you are, as students, are paying too much money for this service to just blow you off. You know, you deserve an answer.
And plus, I don't want to get behind. Like.
Exactly. Okay. Right. We're still early. I thought it would take longer than this. Well, okay, here's the thing. In this course, where our exams are online, we don't have to take up any class time doing exams. And that's one of the reasons that we're ahead. So I don't want to get into any reviews yet because, I mean, we just introduced the material, so you really haven't had a chance to look at the example problems in the review document. And once you get into those, then you may have other questions. So the next time we meet on Tuesday, we'll do a review. And between now and then, you're welcome to, let's see, this is, well, I have office hours this afternoon. That probably won't help you much. But if you need a Zoom session to answer questions, then just let me know and I'll send you an invitation with a link, and you just click on the link and we'll pop up a Zoom session. And you can contact me on the weekends too. I'm a little harder to get in touch with on the weekends, of course, but I'll get back to you probably within a couple of hours at the latest. And we can, because all my emails are linked to my phone, I eventually get them. There's some lag time in there, but eventually I'll get your message. Okay. Well, I can't see holding you another hour when there's nothing more to talk about.